Hello everyone. We've been learning about similar triangles in the past two videos. What we saw so far was that when two triangles looked similar when their corresponding angles were equal. I'm just drawing two triangles, one big and one small. The shapes of the triangle are the same because the angles were maintained. That is, the vertex angle here was equal to the vertex angle here. This angle was equal to this, and the third one also. That is, the corresponding angles were equal, and so they looked similar. Similar in the sense the shapes were the same. Though the sizes were different, the shapes were the same. We'll just call the triangles ABC and FDE, and as their corresponding angles were equal, we found that the triangles were similar. FDE was similar to triangle ABC. This was the sign used for similarity. And in the process of doing that, we just guessed that the corresponding sides were in the same ratio. AB by FD was equal to AC by FE was equal to BC by DE. The ratio between the corresponding sides were maintained because if they were not the same, then the triangles wouldn't look similar. They would not look similar at all. Now in this case, since the numerator is bigger than the denominator, that is ABC, this triangle is a scaled up version. This is a scaled up version of FDE, so this ratio would be greater than 1. If you compare a smaller and a bigger triangle, the ratio would be lesser than 1. For a scaled down version, it would be lesser than 1. But in the case of the ratio being equal to 1, we call them congruent triangles. But here we are talking about the ratio being the same, not being equal to 1. We are talking about similar triangles. Now what we did in the end of the first video, we tried to shift the small triangle and place it on the second, the larger triangle. And in the process, we found that two of its sides, the bases of both the triangles were parallel to one another. And hence in our second video, we made a figure like this. We drew a triangle, say ABC, and we constructed a line parallel to BC, calling it DE. These two lines we constructed parallel to one another, and we went through a very formal proof, and we proved that this line, which was drawn parallel to any one of its sides, divides the sides in a specific ratio. That is, AD by DB was always found to be equal to AE by EC, provided that DE was parallel to BC wherever DE was situated, or wherever, even if DE was here in this place, this ratio was maintained. AD by DB was equal to AE by AC. And this is popularly called as the Basic Proportionality Theorem. Now, we are going to use this Basic Proportionality Theorem to prove our intuition that the corresponding sides of a similar triangles are in the same ratio. So let's proceed to prove. For that sake, let us consider these two triangles once again. We have to prove this. This is what we'll have to prove now, isn't it? The ratios, the corresponding ratios are same. Now, we could have done it by superimposition, of course, but since we need to put it on pen and paper, let me measure FD with a compass. Using a compass, placing the needle of the compass on F, measure FD, the length of FD, and cut an arc on AB at D, such that FD is equal to AD. And in the same way, using the compass, measure FE, the length FE, and cut an arc on AC at E. We are doing something similar to superimposition, just to do it in our notebooks. FE is equal to AE. So what have we obtained? We have obtained a same triangle here, FDE. Just by joining this DE, we have obtained the same triangle. So these two triangles would be equal, congruent, I should say. Of course, you can prove the congruency because angle F is equal to angle A. Let me put it in a separate color. angle F is equal to angle A, and FD is equal to AD, and FE is equal to AE. So by the SAS postulate, these two triangles are congruent to one another. So we can conclude that these two angles, D and B, are the same, isn't it? And E and C are the same, because a triangle FDE is congruent to triangle ADE. We can say that these two angles are same, right? Now, this also we have AD by DB is equal to AE by EC. Right, these two triangles are similar also, ADE and ABC, but we'll come to it. We'll have to prove that these corresponding sides are in ratio. So from this figure, we infer that AD by DB is equal to AE by EC using this theorem, the basic proportionality theorem. But what we need is, we need an AB and AD, right? We need AB and FD. Yeah, we need this AB, and this FD to prove this result which we want to prove. So somehow I will have to manipulate this here and bring it to AB and AC, etc. So let's try to do that. In order to do that, I think the AD portion has to be there. We need the AD portion because AD is equal to FD. So let me just invert this. The ratio holds the same even if I invert the ratio. DB by AD is equal to EC by AE. Why am I inverting it? Because I want AD and AE to still appear in this ratio, and it would appear only if it is in the denominator, because we are going to add 1 to both sides. Why are we adding 1? So as to bring in AB and AC. Now see how we are bringing in AB and AC. What happens by adding 1 to DB? Because the denominator is AD, you get DB plus AD by DB, right, is equal to EC plus AE by AE. Sorry, this is not DB. This is AD. I'll have to copy the denominator as it is. I cannot alter the denominator. So this is AD and this is AE. Only the numerator we have added because of LCM which we have taken. So what is DB plus AD? Just look at the figure. This is AD and this is DB. What is DB plus AD? It is AB, right? So DB plus AD is AB. And let me write AD as it is equal to, similarly look at the other side, what is EC plus AE? This is EC and this is AE, so EC plus AE is AC by AE. So this is what we have obtained. And now still have we obtained this? No. We have AB by FD here, but look at FD and what we have obtained here, AD. FD and AD are the same. This is by our construction. So we'll just replace these two equations here in the numerator, in the denominator. So what do you get? You get AB by FD. AB by, instead of AD, let me write FD is equal to AC by, instead of AE, let me write FE. See? We have, let me bring this down so that you can compare. Yeah, bringing it down here. See, for your comparison, we have almost arrived at it, but for this third BC by DF, the other two, AB by FD is equal to AC by FE, we have arrived at the first part of what we had proposed, that the corresponding sides are in proportion. So just the third part remains, which is very easy. Instead of consider the same two triangles. Let me draw the same two triangles here quickly. This is the smaller one and this is the bigger one. This was FDE and ABC. Instead of measuring arcs equaling FD and FE, let us this time use the center as D. Let me change the color. Using the center as D, measure DF, and from B, cut an arc here and call it F. And same way, using the center as D, measure DE with this as center, cut an arc here, EF. Now, see, the story repeats again. You have a line which is parallel to AC, EF is parallel to AC, so BF by AF is equal to BE by EC. We start from here, and finally you would end up proving that AB by FD, this AB by FD is equal to BC by ED, right? That is what you have here, yeah, BC by ED, yes. Why have I written DF here? FD, FE, and it should have been DE. It got cut while I brought it down, DE. So you would have obtained, using the second figure which I have drawn here, AB by FD is equal to, this is AB, this is FD, is equal to BC by DE. But before obtaining this, you will have to go through all these steps once again, which I am sure you will be able to do. So look at 1 and 2. We have proved this whole thing, which we wanted to prove, that the corresponding sides are in the same ratio if the corresponding angles are equal. And of course, in your textbooks, you wouldn't have these three videos logically placed like we have done it here. You've just given theorems and proofs on the beneath the theorems, but in the last three videos we have tried to provide a whole connection. We have tried to provide a connection between this basic proportionality theorem, the definition of similarity, and using both of them to arrive at the corresponding sides of similar triangles being in the same ratio. I hope you appreciate these videos. Thank you.